So our final speakers for today are Volkmar Sturzing and Dr. Mark Weber from Siemens Technology. Volkmar is the research group is in the research group learning systems at Siemens and brings over 30 years of experience in the neural network and machine learning field. In 2017, he was awarded Inventor of the Year at Siemens for applying RL for continuous gas turbine tuning, which is super cool to hear. And this application has now become a product of Siemens Energy. Mark Weber is a senior key expert for AI-based control optimization, and his work at Siemens focuses on driving applied machine learning topics and solving control optimization problems for the industrial domain using AI and reinforcement learning. They'll share how Siemens is bringing RL to industrial problems in a reliable, trustworthy, and cost-efficient way. And they'll also discuss RL use cases that might impact you every single day. Starting with RL-controlled power plant gas turbines, we'll introduce typical requirements from the industry and present derived research and software results. So that sounds like a really great sort of follow-up from the presentation that we had just saw, and really excited to learn more. Thank you both.
Thank you very much. Can you hear me? Thank you very much. Can you hear me? Okay. We are going to present what we are doing at Siemens with reinforcement learning in the physical world. Let's look at the system, the situations that we are typically facing. We have systems that operate in the real world, producing log files, sensor data, sometimes supported with simulation models such as digital twins. And those observations that are provided are typically then derived from the plant, from the system, and form the basis for our work, which maps typically to offline reinforcement learning. So we need to extract the dependencies, build our own models, our simulation models. We typically use genetic programming or swarm optimization, neural network methods to, on the one hand, learn the system operation, the system behavior, but on the other hand, of course, build a reinforcement learning control policy. However, before this reinforcement learning control policy can be really deployed on the real system, our task is to verify that the operation is correct. Typically, that's being done used on trajectories of the regular operation that was recorded. So we can already get impression on how a real policy will operate the system, what will be the improvement potential which we will be able to exploit before we deploy the system, the policy on the real system, where it modifies the action, where it controls the system in a different manner. If we look at how our work has developed over the years, of course, we were inspired by the work of Sutton and Bartow and the TD Gammon in the 90s. And our first system we looked at was a washing machine, where task was to best distribute the laundry when the washing machine starts spinning. And really, we figured out that we were able to build control policies, reinforcement learning control policies that control the drive accelerating faster or slower, that were actually better than the best hand-engineered strategies. So this was definitely encouraging. However, it also pointed out that if we want to learn from such systems, we needed an engineer which actually tweaked the drive to run faster or slower, doing this manually. So data efficiency was a real issue already at that time. Then we moved from, let's say, 50-pound, 100-pound system to a million-pound system, which is a gas turbine, where the crucial nonlinear and stochastic task was to control the combustion process inside the gas turbine. So you're speaking of 20 bar pressure, 300 psi at temperatures of 3000 Fahrenheit, 1600 Celsius. And you control the flame by distributing the natural gas, the methane, on different nozzles that shape the flame essentially. And in 2017, we installed this on the largest Siemens gas turbine, the 8000H, and operated it there. In 2019, we invested into uncertainty aware and interpretable reinforcement learning. And this was then applied to control the polymerization reactor, where we were able to derive an interpretable control policy from less than 100 data points and deployed it on the process control system PCS7 of Siemens. A different application in the mobility domain is something Mark will later speak about, but of course, the crucial topics and the technologies we were first to invest in and really did our own research publications on are data efficiency, of course, then having some control by the operator in the sense of a variable objective policy, but also the interpretable reinforcement learning, uncertainty aware reinforcement learning, and approaches to provide safe operation. In the international side, you all know about AlphaGo and the successes there, but I personally find the most interesting one quite recently the control of the tokamak fusion reactor plasmas by modifying the current in the coils to form such a plasma. And that approach on physics-informed model-based reinforcement learning by DeepMind was really very interesting and I find highly inspiring. Now let's have a look at what are typical differences between what's being done in the industry domain and in the research domain. In research, our understanding, our feeling is that frequently there are unsolved problems and pretty much uncharted territory, which you are tackling. On the other hand, in industry, you are typically encounter systems which are operating. They are therefore have we call it default control policy, a default operation, which typically is not that bad, but your challenge becomes to get better than that one. And for this, you have limited data, domain experts which have some understanding, and you need to build a safe but also interpretable and trustworthy solution, which might run for years. On the other hand, in research, you have a fast-moving and competitive research field. Frequently, you can also start with a clean learning setup. You have maybe an online connection, you can fast feedback loops, you have infinite rollouts, and frequently also unlimited sampling capabilities. Whereas in industry systems, typically you need to use offline data. You cannot just run turbine differently and trying to learn something, meaning I try something, I don't know if it helps. It might risk your system. Nobody would let you do that. So you have the necessity to integrate domain know-how, also constraints to come up with a definite safe operation, which still exploits the optimization potential. And of course, this all needs to be done in time and budget constraints to not jeopardize your business case. Now let's look at the application examples. I will start with the gas turbine and then hand over to Mark with our other use case examples. After we had some success with the washing machine distributing the laundry, I was very keen that based on the nonlinearity, the stochasticity of this operation, also the non-availability of analytical models for the combustion process, which were usable, reliable, I wanted to tackle gas turbine. And a £1 million gas turbine producing 300 megawatts of electrical energy, that's kind of the order of magnitude you need to supply San Francisco with electrical energy, is definitely a challenge. We use the data records, we identified dependencies, of course, verified this against domain experts, and built our own models, which proved pretty well, which not only indicated the proper operation of the combustion, but also allowed us to verify how our operation is doing. The challenge is to, on the one hand, reduce NOx emissions, while on the other hand, have the competing goal of the combustion dynamics on clear bounds, not exceeding certain limits. Otherwise, you could risk damaging the turbine, and this would be a very expensive experiment. So when we first deployed this and tried to operate the turbine, actually minutes before the operation, I got the guidance, so switch on your policy, but please have the turbine control policy not do something really. It should just run, but it should not do too much. Now, of course, you can all imagine if you have a control policy trained on optimizing a system, it has a plan on how to do it and what to do. You cannot easily say, just don't do something, but try to do something. And actually, we switched it on. The turbine was at a good operating point, and when it was activated, the policy really reduced the NOx emission significantly, as you saw, by moving to a different control setting, which was really successful. And actually, that was then basis for creating also a product which now runs on more than 10 gas turbines of various frames. And if you enter at Google gas turbine and auto tuner, you will be linked also to the product offering from Siemens Energy. And now I would want to hand over to Mark Weber for the next two use cases.
Yeah, thanks a lot, Volkmar, and happy to join the session also tonight, at least in Germany. Yeah, since we figured that probably not every one of you has his or her own gas turbine at home, we also wanted to pick some more tangible project and use case example here, and we did so with hopefully a scenario that every one of you knows. It's early in the morning, you already get late to the subway station, and once you get down there to the platform, you see it's a huge mess. Crowds of people on the platform waiting for the next train to arrive. And once this train arrives, it's completely packed. Everyone tries to squeeze in, while then the subsequent train is usually pretty empty and convenient to ride. That's definitely one of the situations you want to avoid, and also the operator for such systems wants to avoid. And Siemens, as a large manufacturer for subway trains and also subway stations and networks, of course, wants to support its customers in doing better. So we picked this very interesting project, and we found it a perfect challenge for reinforcement learning application for several reasons. So one of the things is that we have multi-objectives at hand here. One is, as I already mentioned, to optimize the time schedule adherence, while at the same time avoiding peak situations or even oscillations in your distribution of passengers and delay times. On the other hand, the operator also has a strong economic interest in creating power savings. And there's a huge potential, for example, here, because the energy recovered from deaccelerating trains in one part of the subway network can be transferred to trains waiting at the station and wanting to accelerate. So there's like this recovery mode, and in the end, you really want to trade and balance all these KPIs in the best case online and in real time. And these requirements made this, like I said, a very fruitful use case to apply reinforcement learning as the base technology. As I said, such solutions are often not accepted by the customer if it's only delivered as a complete black box. So operators of these subway systems, they typically want to have at least some part of the control at hand. And even if the control is difficult, they want, for example, to give their own preferences. For example, whether in the current situation, the policy should focus on, for example, reducing the passenger peaks, or, for example, focus on energy savings. This brings us here to multi-objective reinforcement learning, also with the idea of providing a large set of different scenarios at training time. You see here on the left-hand side, at training, we could mix into the simulation different topologies, networks of subway systems, time schedules and timetables. And all this was used to generate a broad variation of different scenarios, all simulated in the custom-made and company-owned simulator for such processes that can handle all the stuff mentioned before, which is, for example, modeling the distribution of passengers and the impact on the time schedule, as well as power curve and power consumption properties. In the end, the idea was really to provide a policy that can be adjusted at runtime and still be used sort of in the loop. And the operators then, like on a slider bar, can define whether they want to preference more on the signaling and passenger comfort or on the power saving side. Another really exciting use case, and quite relevant also due to the recent spike in demand for logistic systems, we've seen that, of course, accelerated by the pandemic. The amount of parcels deliveries to be made in the whole world has increased tremendously, and all suppliers of such hardware and software systems to make it faster and more efficient, of course, are desperately trying also to use improvements on the software on the algorithmic side to improve their products. Now, Siemens Logistics is building a really great machine. It's indicated here on the upper right corner. It's called a singulator and separator for parcels and deliveries. And the basic principle is just depicted here on the lower right. Usually you have a load of a bulk of parcels coming in from either side, in this case from the left-hand side, maybe some truck bringing a new delivery of parcels and putting everything on this belt here, on this conveyor belt. And now, of course, you want to disentangle this messy situation. You want to get the parcels separated, rotated, aligned, maybe also aligned along the vertical axis here. And this is possible with a very nice invention, which is this multi-dimensional belt matrix here. You have rows and columns of individual elements. Each can be addressed with its own motor and set to a dedicated speed. And then you can imagine you have a large variety of different opportunities to find a good distribution of speeds that in the end lead in rotations and separations of these parcels. Again, looking at this, and there have been, of course, hand-tweaked and engineered solutions for many, many years, if not decades. This was a great challenge to say, can we build a learning and data-driven reinforcement learning agent that can even surpass a well-tuned policy from human engineers? And this is why the initiative was started to use an RL approach in this case. As Volkmar mentioned, in the early stages, we typically learn on either recorded data, offline reinforcement learning, or on available simulations. In this case, we were lucky to have a good simulation representation of this device. By the way, it's not the one here shown on the right-hand side. That actually is a surrogate model that we learned in one of the intermediate steps, neural net model of the movements, but not even depicting the whole complexity. This is a smaller device than the one we're actually addressing here. And then, of course, the whole idea is based on cameras looking at these scenes and receiving the raw images from the parcel streams to learn an agent placing optimal actions. And at this point, the fundamental challenge becomes obvious. If you just look on this problem from the bird's eye perspective, you would find that there's a highly dimensional action space, up to 84 order 100 dimensional actions to be taken, also a large observation space, of course. So again, here we needed to come up with our own architectures and reinforcement learning algorithms to break this problem down into a tractable position. And well, as you can imagine here, there is some localization issues or properties in this problem. You can imagine that you can also think of local policies acting for each of the parcels individually, and then the parcel only seeing a certain neighborhood and still being able to optimize on a global level. So that were the motivations and ideas to also look at this use case. And it's a really nice example to have multi-agent goal-oriented reinforcement learning that also incorporates, of course, prior domain knowledge that is available for this whole system. Now, after looking at these specific examples, of course, we want to wrap up a little bit our experience. And on this slide, what we try to show is a path that we found in the past to be often more successful than maybe other ideas. It doesn't mean, of course, that the path that we didn't choose is worse, but it's just less suitable for the requirements and the challenges we have to solve in our daily business, in our industrial domain. So typically, given the requirements, which is robustness, repeatability, also cost efficiency, data efficiency, we are very often in an offline reinforcement learning setup. And even there, we find that more robust methods, model-based methods, not even sometimes gradient descent methods, but rather population-based methods provide the most robust and stable descent to a very good solution that can also be challenged, that can be tested and verified better than in many cases the maybe more research-minded approaches of online explorative reinforcement learning or value function-based learnings. As I said, it's not a bias or not a judgment on the general quality of these algorithms. It's really more looking at what works good for certain requirements and use cases. On the side that we investigated, like I said, we are also very often confronted with customers or partners who ask for transparency, who want to understand what is behind a policy and would not accept just a black box. And also for these cases, policy search methods, for example, with evolutionary algorithms, genetic programming is one example, or using gradient-free descent algorithms is one of the key findings that we have done or taken in the past. Just a little example here you see on the left. This is a little real hardware demonstrator we built sort of in our spare time at the lab, a realistic card pole built by our team. And here on the right-hand side, you can see another colleague of ours who trained the invasion neural networks as a model incorporating uncertainties on the various trajectories that can be generated here, and then using this uncertainty-aware network as a representation for a model, and then on top of that apply model-based RL to get to a really stable solution that is also sensitive, or let's say insensitive or agnostic of, for example, changing the friction parameters over time, or certain other aspects that have not been modeled just by the differential equation here of movement. Right, I don't want to bore you with all the science. Of course, in this case, I just wanted to indicate that who's interested can, of course, always approach us. I think there are probably ways to also share this information then in the aftermath. I just want to say that who's interested in more of the previous shown path in research, there are a lot of entry points here, and of course also great research by many others in this field. Well, now coming to the conclusion, we've seen now use cases, we've seen lessons learned, takeaways from all this. Of course, the holy grail still for the whole business is to make reinforcement learning profitable and become a real competitor to state-of-the-art control mechanisms and approaches. For us, that definitely means that all these kind of solutions and algorithms have to generalize better, they have to scale faster and better, and the process of generating a policy must be ever more automated. And in order to do so, we also found a great foundation in the work of Ray and Anyscale and all the pending libraries, which is why internally at Siemens Technology, we started more than a year ago an initiative where we want to use Ray, our LLib, as a platform, as a solid foundation, where we would like to put our approaches, our necessities and requirements into it by providing algorithms and benchmarks as templates and blueprints, hopefully to spread fast within the company and to become also the modules and the cornerstones of new applications. That is really why we are quite fond of having this solid foundation now available with the Ray network. Yeah, with this, I think we conclude our presentation. Hope you all enjoyed it, and yeah, looking forward to your questions.
Mark and Wolfmar, thank you so much for such an interesting talk. I didn't realize there were so many applications of RL in so many aspects of my life, from package delivery. I ordered an iPhone this week. I wonder using tools that you're talking about, and then also the laundry machines.
Absolutely, and it's had such a deep and sort of long. The washing machine example, I think, was listed in like 2003. So knowing that you have multiple decades of work kind of driving this reinforcement learning and experience and investigation is super compelling.
Cool. So we have just a couple minutes for questions. So Mark, I'll probably ask you maybe 2 or 3 questions from the audience.
Sure.
So the first question is, can you talk about the challenges for going from simulation to real, so sim to real transfer, and what in your experience is more important, improving the fidelity and the reality of the simulation, or just or doing domain randomization?
Well, it's a question not easy to answer in this general form. I mean, of course, we have the observation that crappy simulations or missing effects in simulation will be a pain then after you want to transfer the solution to a real machine. I mean, that is the paradigm for all these use cases that rely on simulations that, of course, they must be then transferable to the real system. Also, why we showed, or we actually started the discussion or the presentation more with the offline reinforcement learning scenarios, where the big advantage on the one hand side is that the data comes from the real machine. And for us, I can say that sometimes a mix is actually a desirable approach by taking offline data or having batch-based reinforcement learning, but still try to use a model-based algorithm. And that means you have one step in between. You learn a surrogate model, for example, with neural networks from the data batch that you have recorded. And then you get rid of the, let's say, disadvantages of offline reinforcement learning, which is you cannot explore, you cannot get this interactive feedback, but use your derived simulator. Of course, also here, you need to know the limitations of the simulator. And yeah, so that is generally a true statement. So, I mean, of course, improving your algorithm is important, but if the foundation, I mean, the simulator or the surrogate simulator derived from data is faulty or does not reflect reality, the the algorithm can be as good as it wants, it wouldn't get you to the good solution.
And I'm really curious as well. This is a question from Nicholas. What's the most important thing to keep in mind when building models that can safely run for a long time? I think this also touches on some of the transparency methods that you were mentioning. You know, many of your partners, I'm assuming, want to, you know, have an understanding of what the system is doing and why it's making the choices that it does. So just kind of speaking a little bit about that and whether you've built any tools in-house or if you're using anything kind of off the shelf.
Also, one of the opportunities you have if you have an operating system is that it runs already. So the way it is being run, you could consider as a default policy also with respect to also control variables. And if you are able to agree instead of the current point of how it is being operated to a band within you are safely allowed to vary the operations, the parameter settings, and you get an agreement with the domain experts that this band is safe within to operate, and you can demonstrate yet that you improve with respect to the performance, then this is a method to ensure that you can safely operate it with respect also to what the experts are saying. Now, the other point is that, of course, you might complement the data that you have with clear dependencies or rules for operations where you might be lacking data, but which might be highly important. So typically, you don't want to test your systems at the borders where it might break. So just there, your data coverage might be highly limited. And then there will be rules on how the system should operate. And of course, you can incorporate those into the control policies. So these are two rules, meaning a defined with respect to default policy and safe range where you have limited data.
You want to ask another question, or do we have time for another question?
We have maybe just one last question. How do you sort of think about reproducibility? So Miguel asks, one of the advantages of using traditional control methods is the ability to sort of control the reproducible nature of your experiments. So how do you deal with the challenges when you go to reinforcement learning, these like very, very stochastic simulation-based methods?
Yeah, but I mean, Volkmann, do you want to answer?
Essentially, what you're looking is you are building a model, an internal model of your system, and you are comparing and verifying also the operation of your system with respect to the normal operation of the system. And that is the method which you typically need to use to get acceptance to commission your solution and to make it run in 24/7 operation. Mark, you wanted to add something?
Yeah, maybe adding, of course, that's the trade-off we're trying to do and also trying to convey with this talk here, that to deal with the stochasticity, you need to find or to take some measures. And one example I've shown before is, for example, to make your simulation uncertainty aware, for example, by using uncertainty aware neural network technologies. And then, of course, the reinforcement learning algorithm needs to take advantage of that, meaning incorporating that uncertainty, and that might then not lead to the most optimal solution, so to speak, but something on a Pareto front or in a more robust regime of the optimization space. Maybe a little less performative, but at the same time robust in the sense of more robust against little disturbances in the data distribution and in other features of the real environment.
I love how these last couple of talks especially have touched on kind of how you really bring reinforcement learning models into production in kind of these existing companies that already have established systems. And that's really, really challenging to do. So being able to get your insight into how to do it effectively has been really fun to listen to.